So last time we talked about the RSK correspondence and the corollaries that it led to, which enabled us to write H and E in terms of the monomial symmetric functions. So let me recall the formula for E specifically. It said the following: if you want to write E lambda as a linear combination of the monomial symmetric function m mu, then here's the coefficient. So this becomes summation over mu, n lambda mu, m mu, where n lambda mu is the sum over mu of k mu prime lambda k. Okay, where the k's of course are the Koska numbers, a number of semi-standard Young tableau of shape nu, and so for example this is of shape nu and type mu. Okay, and the other one is shape nu prime and type lambda. Okay, so now the point is that at least in the case of E lambda, this has a nice consequence. So observe that if n lambda mu has to be non-zero, so it's clearly a positive number, non-negative number. But if it's positive, it means that at least there exists a partition nu such that, so by the way, all these sums are over, if you assume that lambda is a partition of D, so recall that was the notation, and mu, so what do the sums run over? So mu runs over partitions of D also, and here nu runs over partitions of D. So I'm fixing some D. Okay, now saying that n lambda mu is positive means there exists at least one term nu in this sum which contributes a non-zero answer. So there exists nu such that k nu prime lambda is positive and k nu mu is positive. Okay, and recall that we had already a condition for at least a necessary condition for when the Koska number can be positive. Okay, so a Koska number is positive implies that, so for example the second guy here, this means that nu must be bigger than or equal to mu in the dominance order. So I'm now talking about the dominance partial order on the set of all partitions. And similarly, the first term implies this, that nu prime is bigger than or equal to lambda, again in the dominance order. Now recall that if nu prime is bigger than or equal to lambda, then so prime, recall, is the conjugate of the partition. This means that if you take conjugates on both sides, then you get lambda prime on one side, nu on the other, because the conjugate of the conjugate is the original, but then the inequality reverses. Okay, so recall this was one of the properties of the dominance order. So now we have this rather nice statement that on the one hand that nu is bigger than or equal to mu, and on the other hand lambda prime is bigger than or equal to mu. In particular, this means that lambda prime must be bigger than or equal to mu. Okay, so what does this mean? It says that if you attempt to expand E lambda as a linear combination of m mu's, then the only possible non-zero coefficients n lambda mu can occur if mu is less than or equal to lambda prime. Okay, so that's the condition here. Okay, so therefore we conclude that E lambda is actually no need to sum over all mu's. It's only those mu's less than or equal to the conjugate of lambda that can possibly give you a non-zero coefficient, okay, times m mu. Okay, so now what does this mean? This is a sort of triangularity statement. Okay, so also here's the other interesting statement which is very easy to check again from the definition. If you put mu equals lambda prime, okay, so that's the sort of the extreme case. So let's go back and see what that would imply. If mu equals lambda prime, then you are trying to look for all nu. So look at what these two conditions will imply. Okay, here we are. So lambda prime was bigger than or equal to nu was bigger than or equal to mu, right? That's how we concluded. But suppose the two ends are equal. If lambda prime and mu are equal, then that means there is only one possible value for nu in the sum, which is nu equals lambda prime and mu. Okay. in which case the n lambda mu just reduces to a single term. So let's go up again. So here's the definition of n lambda mu. The summation here only has a single contributing value of nu, which is nu equals mu, which is the same as lambda prime. Okay. So now let's write that out and see what you get. N lambda prime is, there's only one single term, k nu prime. Okay, so I have, so mu was lambda prime in this case. So this is, so that actually this. So k lambda. So nu is lambda prime, so lambda is lambda. And okay, it's just going to give you this product. So mu is lambda prime here. Sorry, I should have written that as lambda prime. But recall that the Koska number is 1 when the two things are equal. Okay, so this is just 1 times 1, which is a 1. Okay, so n lambda prime is actually a 1. So what does that mean? It says that in fact this is a triangularity statement. Okay, that if you expand e's in terms of m's, then the transition matrix is sort of, upper triangular or lower triangular, however you wish to arrange, with ones on the diagonal. Okay, so corollary is that when you write E lambda as E mu, the mu's that are involved are only those which are less than or equal to lambda prime. Okay, what this means is that you can order the bases. So this is an m. You can order the bases, the e's and the m's, such that they go up on the one hand, that triangularity. Okay, so then statement is that this matrix where lambda and mu ranges over the partitions of T can be thought of as a triangular matrix, upper or lower depending on how you arrange the entries, and it's unitriangular, meaning the diagonal entries are all 1. Okay, in particular this means that this is an invertible matrix, and a corollary is that since the m mu's are a basis, the E lambdas also form a basis of the space of symmetric functions of degree t. Okay, because the matrix is invertible, and we already said this, that the most obvious basis is the monomial symmetric functions. Okay, good. So that's one nice property. Now what I want to talk about next is the generating function for the e's. So what's the generating function for the e? For the en first. So recall what the en was by definition. It's just all sums of variables taken n at a time, and to avoid repetition we assume that they are in, say, increasing order. Okay, and recall we are talking about infinitely many variables, so this is actually a formal power series. Okay, now let's do the following. Let's take t, it will be an indeterminate, meaning it's another variable, and it will keep track of the degree. Okay, so you will see in a minute. So t is going to be some additional variable that we will use. Now let's do the following. Let's consider the following infinite product, okay, which is 1 plus txi. Okay, this is now going to run over I from 1 to infinity over the set of all variables. And if you look at this infinite product, how do we think of it? How does it make sense? Well, you can think of it as a power series in T. Okay, so where does this belong really? So I can say that this belongs to the ring of power series in T, but what are the coefficients? Okay, the coefficients of any given power of T is going to be some polynomial in the exercise. I mean, not a polynomial really, a power series in the exercise. And if you think for a moment, you will realize that in fact the coefficient of any power of T is actually a symmetric function. Okay, So for example, what's the coefficient of t power 1 itself? It's the summation of xi. The coefficient of t square, you have to somehow get t square by pulling out t's from two of the terms, and that is therefore, you take all possible txi times txj over all i's and j's. Okay. So if you sort of think about this for a moment, you realize the following, that, well, this is actually very easy to see that this is the following power series t power n, where the coefficient of t power n is exactly en. Okay, the en in the infinitely many variables x1, x2, and so on. Okay, so this is what's usually called E of t, the power series for the elementary symmetric functions. And this is only, remember, for the en's. So there is something more we will need to get the E lambdas, right? So recall the E lambdas were products of, E lambda 1, E lambda 2, E lambda n. So how does one get E lambdas? Well, one does just a little bit more. So let's consider not just a single indeterminate t, but a whole collection of them, infinitely many of them, y1, y2, y3, and so on. So these are what I'm substituting for t. Okay, so consider E yj's, and let's do the following. Let's also take the product over all j equals 1 to infinity. Now what is this really? This is going to be the product. So each E yj, we understand what it is. It's like an E of t, summation t power n en of x, except I must replace t power n by yj power n. So this is now yj power n, n is equal to 0 to infinity. So we think of it as a power series in the variables y1, y2, and so on, with coefficients coming from the symmetric functions. And again, if you ask what's the coefficient of a certain monomial, right, y1 power something, y2 power something, and so on, then it's just a product of the corresponding ej's. So observe, if I take y1 power n1, y2 power n2, etc., the corresponding coefficient that it comes with is exactly en1 of x, en2 of x, and so on. Okay, so you can really think of this as a power series in this fashion, n1, n2, and so on, ranging over 0 to infinity. Okay, but again, this is symmetric in the sense, if I interchange n1, n2, nk, I take some finitely many numbers and I permute them in all possible ways, then the corresponding en1, en2, that product is the same. And so if you think about it for a moment, you'll realize the following, that I can rewrite this as follows: lambda varying over all partitions. Okay, so this is over the set of all partitions of E lambda of x, that's this product, and the corresponding term that's in the y is exactly going to be the monomial symmetric function m lambda of y. Okay, so this is the final thing that we have concluded here, that if you take 1 plus xi yj, right, this is the product of E yj's. Now this is overall ij's running from 1 to infinity. This just becomes a summation E lambda of x, m lambda of y. Okay, running over all partitions, lambda over all partitions. Okay, so this is the, you can think of this as a generating function for the E lambdas as opposed to the, just the En themselves. Now, it turns out there is a completely analogous picture for the H lambdas, okay, and the Hns. You can, if you recall what Hn was, it was the sum, Hn of x was the sum over all monomials of degree n. This is m lambda of x, lambda running over all partitions of n. And this is, in a sense, all possible ways of forming monomials whose total degree is, so think of it as x power alpha, alpha running over all possible infinite multi-indices, such that the total sum of the powers is n. So this is just all possible ways of combining the powers of the variables x1, x2, xn, and so on, so that the total degree of that monomial is n. And analogous to what we did for E, we can talk about the following power series. So just look at product I going from 1 to infinity. We'll put the t to keep track of the degree, 1 plus txi, t square, xi square, and so on. It's an infinite sum. And now, if you look at how this expands and goes from 0 to infinity, it's going to have t power n, and the coefficient of t power n, how can you get a total power t being n? Well, that only happens if you pull out some term from the first term of the product, some power of t from the second term of the product, and so on, and such that the total power of t is n. Okay, and again, if you think about it, this is just, well, what are we doing really in terms of the x's? You're just taking all monomials whose degree is n. In other words, this is exactly the complete symmetric function hn of x. So this is the other the dual picture, if you wish, and observe that this each term here can be written as a power series formally like this. It's 1 over 1 minus txi, right? That's 1 plus txi square, and so on. And therefore, this can be well, it has some resemblance to what we looked at earlier. So therefore, let me just mention this, that this is a generating function of the h's. Let's call it hn t power n. So I'm suppressing the x's in the hn. This, if you observe, is, well, what was e of t? It was a very similar looking expression, but with 1 plus txi and no inverse. Okay, that was the generating function of the e's. And therefore, we make the following conclusion, that if you multiply h with e with a minus thrown in, then that gives you 1. Okay, so ht into e of minus t is 1. Okay, good. Now what does that mean? Well, you have seen power series manipulations before in the course, and what this really means is that if you take en t power n minus 1 power n multiplied by the corresponding, this should be a 1, and again that's essentially an infinite list of equations, because you can now multiply the left hand side out and compare coefficients of t on both sides, each power of t. What this therefore implies is equations of the following kind, that minus 1 power r er hn minus r is 0. Okay, so this is now for r going from 0 to n, and this is true for every n, at least 1. Okay, for n equal to 0, that's a constant term, which is a 1, but as long as n is bigger than or equal to 1, this equation here holds. Okay, and that's just by multiplying this out. Good. So now what is this? This is really a system of equations. h1 minus e1 is 0. That's n equal to 1 case. h2 minus h1 e1 plus e2 is 0. h3 minus h2 e1 plus h1 e2 minus e3 is 0, and so on. Okay. Now these equations allow you to calculate h if you know e, or calculate e if you know h. Well, how? All you have to do is sort of just invert this equation. So let's do one of them. Okay. So from the first equation I calculate, so let's assume we know h and we want to compute e. So this is e1 equals h1. Okay, now I substitute that into equation 2 and conclude that h2 minus h1 square equals minus e2. So in other words, e2 is h1 square minus h2. Okay, so let's do this here. e3 similarly, if I write this out, becomes h1 cubed minus 2 h1 h2 plus h3. Okay, so this is just by recursively substituting into the next equation, and so on. Okay, and the nice thing with this is the following. What this does, see, what is h1 cube? This is just h corresponding to the partition 1 1 1 by definition. This is 2 times h corresponding to the partition 2 1, h corresponding to the partition 3. Right? Those are really, so, and this is really e corresponding to the partition 3. Okay. So what this says is that each en we can write as some linear combination of the hns. Okay. So the corollary from this computation actually is the following. It says not just en, if you take any arbitrary e lambda, this is actually in the span of the h lambdas, or h mu's. Okay, so let's even fix partition lambda, partition of D. Then if you sort of see what partitions you get on the other side, they are also all partitions of D. Okay, so you first check it for en and see that the h's that you get are all partitions of n. Okay, and then the same thing works when you multiply things out. Okay, so what this really shows is that the e lambdas in general are in the spans of the h mu's. Okay, and what does that imply? So observe, we already knew that the e lambdas were a basis. Okay, so corollary, since we knew that the e lambdas are a basis, and now each of the e lambdas can be written as a linear combination of the h mu's, and the numbers are the same. The number of e lambdas is the number of partitions of D. The number of h mu's on the right side are also equal to the number of partitions of D. So what this means is that the h mu's, mu partition of D, is also a basis. Okay, so that's a nice corollary of this way of writing e's in terms of h's. But there's more. There's a beautiful symmetry in this set of equations. Not only does it enable you to write e's in terms of h's, it also allows you to write h in terms of e's. Okay, and if you sort of see how those equations behave, there is a nice symmetry. So this just says h equals e. Okay, now just doing the same thing from the second equation, you eliminate the h's in favor of the e's, then h2 becomes similarly e1 squared minus e2. Okay, in the third equation, just do the same thing that we did. You'll see that it's e1 cubed minus 2 e1 e2 plus e3. Okay, so what does this mean? It says that if you want to write h in terms of the e's, it's the same equation that you got when you wrote e in terms of h. Just replace h's with e's everywhere. Okay, so there is this nice duality or symmetry between the h's and the e's, that you can replace h's with the e's and still get a similar equation. Okay, and so this is formalized into the following theorem or proposition. So the proposition says that if you take the ring lambda of symmetric functions that we talked about, then on this ring there exists a certain map omega. Okay, what is this omega defined by? You just take the following thing, you take en's and map it to h's. Okay, so recall that if you do this, then and extend it as an algebra homomorphism. So when I say this en going to hn, en1, en2, enk also goes to hn1, hn2, hnk, h lambda also, for all partitions lambda. Okay, just map e lambdas to the h lambdas. Okay, and extend linearly if you wish. Then, if you take this map and you sort of do it twice, okay, then omega square is in fact the identity map. Okay, and why is that? That's because if you now write, in order to compute omega square, you first have to write the h lambdas in terms of the e lambdas, then apply the map omega again. Okay, but because of the symmetry that when you write h in terms of the e's or the e's in terms of the h's, the formulas look the same. Okay, so the consequence it has is that if you apply this map omega twice, then it just gives you back the identity. Okay, and so this is clear from what we said already. And this map omega is an algebra homomorphism. It's a ring homomorphism, if you wish. Again, more or less by definition. Okay, so this sort of map is therefore what you would call an involution. Okay, something whose square is the identity. It's a ring homomorphism, which is whose square is the identity. So we have this map, which is what we call an involution of the ring of symmetric functions. And what does this involution do? It maps h's to e's and e's to h's, e lambdas to h lambdas to e lambdas. And so this involution is often a formal way of going between e's and h's in various settings. So if you know something in terms of h's and you want to change it to e's, then one thing we would do is to apply the involution, okay, and vice versa. Okay, good. So this is the statement about the involution itself. Okay, and so far what we have therefore are the following bases. To summarize, we know the m's. So we have three bases: the m lambdas, the e lambdas, and the h lambdas. So we have shown that as lambda varies over all partitions, this forms a basis for the full ring of symmetric functions for the full space lambda. Or if you restrict to partitions of D alone, it gives you a basis of the degree D portion, lambda D. Okay, so there are these three bases. Now, what we know is this: if you apply the involution omega, it maps E lambda to H lambda and H lambda to E lambda. Okay, and what you could do then is also try and apply the omega to M and see what you get. Okay, it turns out that, so this is sometimes called the basis of forgotten symmetric function. So it's always also a basis because omega is an involution after all, right? It's an invertible map. So m lambda will map to another basis, and that's denoted f lambda, sometimes called the forgotten symmetric functions. And you can pretty much obtain any of its properties by just looking at the corresponding properties of m and then applying omega to that. Okay.